In today's video, we're going to look at trigonometric identities. And identities are statements that are always true for all values that can be plugged in. For instance, a reciprocal identity is a function that deals with the cosecant of theta and sine of theta. And in our last unit, we talked about cosecant and sine being reciprocals of each other. And so this is called the reciprocal identity because this function is always true. It's an identity anytime you substitute an angle in place of theta both here and here. So say the cosecant of 24 degrees would equal 1 divided by the sine of 24 degrees. So any legitimate substitution of an angle would cause this to be a true statement. We know another trig identity that is a reciprocal identity involves the secant of theta. The secant of theta is equal to 1 over the cosine of theta. And our third reciprocal function deals with the cotangent of theta. That will equal 1 divided by tangent of theta. Now you could as well say that sine of theta is equal to 1 over cosecant of theta, that cosine of theta is 1 over secant of theta, etc. And another thing that's nice to see is that the product of these two functions is always equal to 1, which is always the case with reciprocals. If you take a number and its reciprocal, you always get the product of those two values to be 1. So those are the reciprocal identities. Now another set of identities that we need to know are the tangent and cotangent identities. And I'm going to draw a unit circle to help us see where the cotangent and tangent identity come from. So I have a circle, and we'll make it a unit circle so that it has a radius of 1. And I'm going to rotate an angle of theta. That theta could be in degrees or it could be in radians. And if I pick a point on the terminal side of the angle and label it xy, we know that this radius would be 1. And that if I drop that little perpendicular down, we know that that coordinate is x and this coordinate is y. And we remember that from our work with the unit circle that the cosine of an angle is equal to the x-coordinate as we rotate around the unit circle. The sine of an angle is equal to the y-coordinate when we rotate around the unit circle. And the tangent is equivalent to the ratio of y over x. So we can see that we can do a little substitution here to come up with what we call the tangent identity. And the tangent of theta can also be written as not just y over x, but the sine of the angle divided by the cosine of the angle. So that is our tangent identity. Now we also have the cotangent identity, which you would expect is going to look like the reciprocal of that. And the cotangent of the identity tells us that cotangent of theta is equal to the cosine of the angle divided by the sine of the angle, which is the x over y. So we have the reciprocal identities, and we have the tangent and cotangent identities. Now another very important identity for us in trigonometric studies, as well as in our calculus studies, is the Pythagorean identity. And the Pythagorean identities, plural, there will be 3 of them, come from Pythagorean theorem. So if I look at this unit circle representation again, I can see that with my little reference triangle here, that it would hold true that the x squared plus the y squared would equal 1 squared, or 1, from Pythagorean theorem. So if we use our unit circle and deal with the terminal side of the angle going through the point xy, Pythagorean theorem would allow us to come up with this relationship. Now we actually have substitutions that we can make, though, for x and for y that involve trig functions. So we can see that the cosine of an angle is equal to the x-coordinate, so I can do that substitution here. And the sine of an angle is equal to the y-coordinate on the unit circle. And typically when we write Pythagorean identity, we write it in a little bit different notation. It would say that the cosine squared of an angle plus the sine squared of an angle is equal to 1. So that's our notation of putting the little square here right up above the s or the n, and that's going to denote that that means the same thing as squaring the entire function. Don't just put the square and drop the parentheses. That would mean the angle's only squared if I put the 2 right in that position here. Don't want that to happen. So this is our first Pythagorean identity. Now, if we take this function and we divide the entire function through by the cosine squared of theta, so divide all 3 of these terms by the cosine squared of theta, we'll get a second Pythagorean identity. So if I divide this term by cosine squared of theta, I would get 1. If I divide this term by the cosine squared of theta, I have sine squared of theta over cosine squared of theta, and that will become tangent squared of theta. And then if I divide this term by cosine squared of theta, 1 over cosine squared of theta will become secant squared of theta. And this is our second Pythagorean identity, which again you can see comes from the original one. Now if we take this function and divide it by sine squared, and divide both sides of the equation by sine squared, or each of these terms by sine squared, we come up with our third Pythagorean identity. So if I divide this term by sine squared, cosine squared divided by sine squared will become cotangent squared of theta. Sine squared divided by sine squared will become 1. And 1 divided by sine squared will be 1 over sine squared, which can be rewritten as cosecant squared of the angle. So these are our 3 Pythagorean identities. The identity word, once again, means that regardless of input, this will always be a true statement. So if I took a calculator, and it doesn't matter what mode we're in, if I take my calculator, I happen to be in degree mode now, I'll leave it as that. And if I take my calculator and get it over here in the center, if I hit left parenthesis cosine of, say I take 423 degrees, get that quantity squared, plus take the left parenthesis here, the sine of 423 degrees, and square that quantity, I get 1. If I do second entry, I could change those angles to whatever I want. Say this time I just put in 7 pi, delete that little character, go over here and change this to 7 pi, delete that character, and hit enter, I'll always get 1. Okay, so regardless of input, and regardless of whether you have this in degrees or radians, this would have been actually still in a degree mode, you're going to always have 1, and that's what means identity. So it works for all angles. Now, we want to use our identities to do some simplification, and then shortly on the next video we'll do some proving of some theorems. Okay, so we want to look at secant of theta and cotangent of theta, and we want to simplify this expression down so that it comes down to one trigonometric function. So we have secant of theta, and we have a few different substitutions we can make for that, but the easiest one to make would be to call secant of theta by the reciprocal function 1 over the cosine of theta. Now, cotangent of theta could be simplified to 1 over tangent of theta, or we can use our cotangent identity and substitute cosine of theta over sine of theta. And that would be the best move to make. Make sure you continue to stay in the same variable and don't start changing it to x's or start dropping the angle off. You need those there as the variable. Now, this cosine of theta will cancel that cosine of theta, giving us 1 over sine of theta. However, the reciprocal identity allows us to change that back to cosecant of theta. You may want to turn the video off and do this one on your own, and then turn it back on to double check. So for cosecant of theta times tangent of theta, we know we can make a trig substitution, a reciprocal trig substitution, and call that 1 over sine of theta. tangent could be 1 over cotangent of theta, but it's also sine of theta divided by cosine of theta. The sines will reduce down. I'll have 1 over cosine of theta, which our reciprocal trig function will allow us to change to secant of theta. Now on C, now I start to have some squares within my expression. And again, these are not equations. We are not solving these. We're just simplifying these down. So you have to be careful about doing the appropriate algebra. We cannot cross these cosine squareds off. This is a 1 minus this factor, so we are not able to cancel and reduce this. If this had been a time sign, then we surely could have reduced it down. So now anytime you have a square on one of your trig functions, remember your Pythagorean identities may be useful. Cosine squared, sine squared, tangent squared, secant squared, cotangent squared, cosecant squared. We have an identity that involves all of the functions in a squared type of technique. Now, I'm going to look at the original identity of cosine squared minus sine squared equals 1. This identity may actually show up, however, in funny forms. If I take this function and I solve for cosine squared by subtracting sine squared from both sides, I should always be looking for something like this to happen. If I have a cosine squared sitting someplace within my question, this substitution could always be made because of Pythagorean identity. Or if I see a 1 minus sine squared of theta someplace, we could always make the substitution and substitute cosine squared in place of it. Likewise, if we see sine squared of theta sitting somewhere, sine squared would be equal to 1 minus cosine squared, just doing some algebraic manipulation of the original formula. So if I see a 1 minus cosine squared sitting someplace, this substitution can be made in place of it. And that's a wise move to make up here. So my numerator, 1 minus cosine squared of theta, is actually equivalent to sine squared of theta because of a Pythagorean substitution. My denominator, yes, I could do a substitution here, but that would kind of defeat the purpose of making the substitution in the original one. I now just leave that one alone. Now, I don't necessarily need to show this step, but I want to show that this is a possible way for some people to make more sense out of this. This algebraic expression of having the sine squared over the cosine squared of that same angle is algebraically equivalent to that. So the sine over cosine of the angle we know would reduce to the tangent of the angle by the tangent identity, and because it's squared, this simplifies to the tangent squared of theta. So if you substituted numbers into this expression, the original expression, say put 17 degrees in here or here, that would give you the same answer as if you substituted 17 degrees in here. Okay, so these algebraic expressions are equivalent. Letter D, you can see a kind of a similar type of situation that you have something that you can use to substitute in place of 1 minus sine squared of theta. 1 minus sine squared of theta we know would be equivalent to cosine squared of theta. Tangent squared of theta can be written as 1 over cotangent squared of theta. However, I wouldn't have any reduction that would take place from doing that. Nice move to make is to use my tangent identity. And we know that the tangent squared of the angle would be the sine squared of the angle divided by the cosine squared of the angle. This is over 1. When we multiply, we can do the reduction before we multiply across. These will reduce down, and I end up getting sine squared of theta. So this original expression is algebraically equivalent to sine squared of theta. And we'll finish up by doing the last two on the next side, and then that will be, you'll be ready to do assignment 1. Now, on letter E, there are a few different things you can do on this question. It's possible to, as I said earlier, anytime you see a square, be suspicious that you can do a substitution with one of the Pythagorean identities. Another thing you can do is split this up into two fractions. If you have something like a plus b over c, it is possible to rewrite that as a over c plus b over c. So another move could be to split this up into two fractions and see if I could do some simplifying there. However, I do see something else that I can do. My numerator is actually equivalent to secant squared because of the Pythagorean substitution. And now my variable is x, so I have to be careful not to use thetas as I had been using on the previous side. My denominator cosecant squared of x. So I have it a little bit simpler. However, we'll have to see if we can do some more substitutions with this. Now, the secant squared of x is equivalent to, by the reciprocal identity, 1 over cosine squared of x, and the cosecant squared of x is equivalent to 1 over sine squared of x. So now we have a complex fraction, but that's no problem. We can invert and multiply. And we'd have sine squared of x over cosine squared of x, which end up equaling tangent squared of x. Okay, and in our last one, another thing you'll want to be cognizant of is doing algebra. Sometimes it's not as evident when you have functions that are in a trigonometric form, but this question is very similar to one that if I gave you something like this and I asked you to simplify that expression down. Okay, in this case, you would factor out the common factor of a. Down here, I factor out the common factor of cosine of x. And then when I do, I have 1 minus cosine squared of x left. Now, I see 1 minus a cosine squared of x, and anytime I see a square, I'm always thinking that possibly a Pythagorean substitution, and I definitely have a Pythagorean substitution I can make here. The cosine of x just comes down. This is equivalent to sine squared of x, and I really don't have anything else I can do. There isn't a way to manipulate this so that I can get, say, a tangent to come out of this or any other type of trig function. So here's an example where sometimes you do a little bit of simplification. I had two factors up here, or two terms, a binomial, and I got it at least down to a monomial, one term. It just happens to be the product of a couple functions. So now you're ready to practice.